All of the important men were there. Groves, Oppenheimer, Chadwick, Courant, and Fermi. Off in the far distance stood a steel tower, at the top of which was the gadget. At the center of the gadget was 13.5 pounds of a plutonium-gallium alloy that had been coated with nickel in the shape of a sphere. Around that sphere was packed a series of 3 shells of high explosives that would initiate the detonation of the product of 5 years of hard work in tense conditions. Everyone was afraid of a fizzle, an incomplete detonation of the gadget that would mean that a mistake had been made in the calculations or design somewhere. The test was supposed to have taken place at 4 a.m., but rain had pushed it back about an hour and a half. At the appointed time, however, in the New Mexico desert, the go-ahead was given, and the sequence was initiated. Enrico Fermi wrote a memorandum documenting his observations of the event. Quote, "On the morning of the 16th of July, I was stationed at the base camp at Trinity in a position about 10 miles from the site of the explosion. The explosion took place at about 5:30 a.m. I had my face protected by a large board in which a piece of dark welding glass had been inserted. My first impression of the explosion was the very intense flash of light and a sensation of heat on parts of my body that were exposed. Although I did not look directly towards the object, I had the impression that suddenly the countryside became brighter than in full daylight. I subsequently looked in the direction of the explosion through the dark glass and could see something that looked like a conglomeration of flames that promptly started rising. After a few seconds, the rising flames lost their brightness and appeared as a huge pillar of smoke with an expanded head like a gigantic mushroom that rose rapidly beyond the clouds, probably to a height of 30,000 feet. After reaching its full height, the smoke stayed stationary for a while before the wind started dissipating it. About 40 seconds after the explosion, the air blast reached me. I tried to estimate its strength by dropping from about 6 feet small pieces of paper before, during, and after the passage of the blast wave. Since, at that time, there was no wind, I could observe very distinctly and actually measure the displacement of the pieces of paper that were in the process of falling while the blast was passing. The shift was about 2.5 meters, which, at the time, I estimated to correspond to the blast that would be produced by 10,000 tons of TNT." Unquote. In that moment, the past slipped away, and a new era dawned on humankind.
Hello, and welcome to the Scientific Odyssey. The Scientific Odyssey is a many-part journey into the history and philosophy of science. My name is Chad Davies, and I'm the writer, host, and producer of the podcast, where we consider the ideas, processes, and results of over 2,500 years of scientific inquiry and discovery.
Series 2, A History of the Atom. Episode 21, A New Era. In this episode of the podcast, I'd like to do a couple of different things. First, I'd like to take a look at the developments in nuclear physics that led to the creation of atomic energy technologies from a scientific perspective. Much of this will be a fleshing out of the broad outlines described in the second part of the Fermi biographical episode, along with some of the other biographical things that I've done, especially on Heisenberg. Second, I would then like to take a few moments to discuss some of the implications of the development of these technologies on how science was done, and some of the philosophical issues raised by the environment in which these and future technologies were created. As I mentioned in the previous episode, Otto Hahn and Fritz Strassmann had shown the presence of barium in samples of uranium they had bombarded with slow neutrons. Lee Smeitner and Otto Frisch had successfully explained and demonstrated that the reason the barium was present was that the uranium nuclei had absorbed some of the neutrons and had then split into smaller pieces. This news traveled to the United States with Bohr, while it reached the Juilliard Curies at the Radium Institute in Paris through traditional channels of academic communication. One of the very important results of Meitner's calculation was that due to the fact that the binding energy of the products of the fission reaction were lower than the binding energy of the original uranium atom, energy was released by the reaction. Most of this energy was turned into energy of motion for the two fission products, but some of it was released via high-energy gamma-ray photons and some with the release of additional neutrons. Most of the research done in the following few months of the announcements was a combination of refining the theoretical modeling of the process using Bohr's liquid drop or compound model of the nucleus, and experimental work to provide the necessary data for the theoretical explanations. In this, the team at Columbia that included Fermi was particularly successful in understanding the process more fully. Much of this success can be attributed to both Fermi's experience with these sorts of systems and his ability to function at a very high level both as a theorist and an experimentalist. The outcome of this research was something very interesting. It turned out that the situation was more complex than anyone thought. To better understand why, we need to do just a little bit of review. If you will recall, it had been known since the work of Frederick Soddy that an element could have more than one what we call an isotope. When an element has isotope, what that means is that each isotope of the element behaves in chemically identical ways, but each one has a slightly different atomic mass. Over the course of the following few decades of research after Soddy's work, it was understood that the number of electrons an atom had, especially those electrons in the outermost energy levels, to use Bohr's old quantum model terminology, are what determine the element's chemical and to a large degree physical properties. The number of electrons orbiting the nucleus, of course, was equal to the number of protons in the nucleus. What made each isotope different was that the atomic weight of each isotope of an element was just a bit different due to a different number of additional things beyond the protons in the nucleus. When Chadwick discovered the neutron in 1932, it was recognized that the specific mass had to do with the number of neutrons the isotope had. So let me give you an example of this. If an atom has 6 protons in its nucleus, it's carbon. Because the typical carbon atom is electrically neutral, it must also, therefore, have 6 electrons orbiting the nucleus in a particular electronic configuration that gives the carbon atom its specific chemical properties. It turns out, however, in nature there are found to be 3 different isotopes of carbon: carbon-12, carbon-13, and carbon-14. What distinguishes these is that carbon-12 has 6 neutrons, plus 6 protons, which is why it's carbon-12. 6 plus 6 equals 12. Carbon-13 has 7 neutrons, and carbon-14 has 8 neutrons. When a researcher has a sample of naturally occurring carbon, say 1 gram of the element, 99% of it will be carbon-12. About 0.9% of it will be carbon-13, and just a trace of it will be carbon-14. Now, in nature, there is almost always an isotope that is stable in that it does not undergo any form of nuclear decay. In atoms with small numbers of protons, this is usually when the number of protons and number of neutrons is the same, as is the case with carbon-12. As one goes to elements with larger numbers of protons, the number of neutrons required to hold the atom together becomes greater. As you get to the elements with the number of protons greater than 89, it turns out that every configuration of the nucleus is so large that some form of radioactive decay will take place, and there is no radioactively stable isotope of that element. This is the case with uranium, which has 92 protons in its nucleus. Now, it turns out that in naturally occurring uranium, the most common isotope is the one with 146 neutrons. If you had 92 protons to 146 neutrons, you get an atomic weight of 238 nucleons. And so that isotope is known as uranium-238, or just U-238. Just about 99% of the uranium found on Earth today is this isotope. However, 0.7% of uranium is an isotope known as uranium-235, and about 0.3% is the isotope known as uranium-234. So when a scientist bombards a sample of regular uranium with neutrons, the neutrons actually have 3 different types of nuclei that they can interact with and be absorbed by. As it turns out, each one of these different kinds of nuclei has different behavior when hit with a neutron. What Fermi and Bohr figured out through the combination of experimental data and theoretical modeling we discussed was that large nuclei with an even number of neutrons were much more stable when they absorbed a neutron than those types of isotopes that had an odd number of neutrons. In other words, when an atom of U-238 absorbed a neutron, it would not undergo fission the way U-235 would, unless the neutron was moving very quickly. What this meant was that those experiments that had used Fermi's slow-moving or thermal neutrons were only able to cause fission in a U-235 isotope atom. The U-238, if it absorbed the slow-moving neutron, would simply become U-239 until it underwent some form of radioactive decay. We'll return to this latter process in a bit, as it's very important for what will take place later in the story. This was why, by the way, Fermi had such a difficult time trying to determine what the result of his bombardment experience had been. Only a tiny fraction of his sample was undergoing fission, a percentage much smaller than the likely impurities in the sample he had started working with. It was only with the higher grade samples and better chemical separation techniques employed by Hahn and Strassmann that the true picture would eventually emerge. Now, once this important detail was understood, the specifics of the U-235 reaction were investigated much more thoroughly. What everyone wanted to understand was how many neutrons were produced when an atom of U-235 split due to absorbing a neutron. Theory suggested that multiple neutrons would be emitted from the fission of a single U-235 atom, but there were a lot of questions of just how many and what would the characteristics of those neutrons be. The research teams at both Columbia and in Paris were able to determine that the number was between 1 and 3 neutrons depending on the specifics of the absorption, and most of the emitted neutrons were moving too fast to be absorbed by U-235. In fact, they were much more likely to be absorbed by the more abundant U-238 atoms. This result, however, was the first observational evidence that supported Leo Szilard's idea from way back in 1932 that a nuclear chain reaction was, at least in theory, possible. As a reminder, a chain reaction is where one fission event gives off multiple neutrons, more than one of which, on average, causes a new fission event to take place, which causes the reaction rate to grow exponentially. Now, what is possible in theory and what is actually doable are two very different things. There's a joke in nuclear fusion research that a nuclear fusion power reactor is just 30 years in the future, and always will be. Get the joke? 30 years in the future and always will be? Okay, so maybe it's a weak physics joke. But the idea is that while the theoretical physics to create a self-sustaining nuclear fusion reaction that will produce more power than it uses is fairly well understood, the practical engineering aspects of creating this reactor that can utilize the theoretical understanding has proven to be a tremendously daunting task since the first attempts were made way back in the 1950s. In our present context, just because Szalard's chain reaction was possible, that didn't mean it was doable. The fear was, of course, that now that the possibility existed, the most scientifically advanced country in Europe, Germany, would attempt to develop it with potentially dangerous outcomes. This is where the two paths of nuclear energy become much more obvious. If one were to produce a chain reaction where the reaction rate of the nuclear fission was allowed to grow to a certain level and then controlled at that level so that the future growth of the number of fission events was zero, the energy released by the reaction could be used to heat what is known as a working fluid that could be then used to spin a turbine in order to generate electricity or do some other type of work. This is the idea of a nuclear power plant reactor. The other path, the one that's a little more dark, is to engineer a configuration of material where the chain reaction is allowed to grow unchecked and rapidly, releasing a great amount of energy in a very short period of time. This device could be used as a weapon, something Szilard and his friend and colleague Eugene Wigner feared the Nazi government in Germany would do. As I've mentioned previously, it was this fear that led Szilard and Wigner to draft the letter to which Einstein affixed his signature that was delivered to the U.S. President Franklin Delano Roosevelt. Recognizing the concerns of the two European refugees, Roosevelt formed a committee to look into how to best proceed with fission research and provide a small amount of funding and material towards that end. This Uranium Committee, as it was first called, would eventually be renamed the S1 Committee and then be absorbed into the U.S. Army's Manhattan Project as the Science Advisory Group and Theory Group for that project. It would be a mistake, by the way, to think this work was proceeding only in the United States. In Great Britain, scientists there were being drafted into what was known as the Tube Alloys Project to investigate nuclear technologies with the express purpose of solving the technical hurdles to producing a weapon. Due to the isolated position of the United Kingdom, especially after the fall of France, British scientists were heavily recruited into the war effort, especially in the areas of radar and weapons production. As also discussed in the third Heisenberg biographical episode, Germany began investigating these sorts of phenomena under what was known as Uranium Club. It was a working group that was soon joined and then led by Heisenberg. This project worked initially on many of the same ideas as the group at Columbia. Though there was an initial attempt to determine if a weapon could be produced, Heisenberg's early calculations said that such a thing was industrially infeasible for reasons we'll discuss in a moment. And so the focus there was turned towards reactor construction. So what are the big technical hurdles to a project like this? The biggest difficulty has to do with getting enough material that is called fissile. For a reactor construction, this isn't so difficult as long as one can get both a reasonably good sample of uranium that is free of most impurities and a good moderator. The two most available moderators at the time were either ultra-pure graphite or what is known as heavy water. So what is heavy water? It turns out that hydrogen has three naturally occurring isotopes. One with a single proton in the nucleus, one with a proton and a neutron in the nucleus called deuterium, and one with a proton and two neutrons in the nucleus called tritium. Regular water is, of course, made of two regular hydrogen atoms and one oxygen atom, or H2O. Heavy water is made of two deuterium atoms and one oxygen atom, and it's sometimes instead called D2O. This particular combination is very good at moderating or slowing down fast neutrons without absorbing them the way regular water tends to. Fermi's group, working first at Columbia and then later at Chicago, followed the advice of Leo Szilard and decided to use ultra-pure graphite, while the German and British projects decided to work with heavy water. The problem with heavy water is that it's really difficult to produce, and so Germany's supplies of this were limited until they occupied Norway. Throughout the war, one of the Allies' biggest priorities was disabling the Norwegian heavy water production facilities. For Fermi's group, the bigger problem here was getting large enough quantities of high-grade uranium. As graphite wasn't quite as good a moderator as heavy water, the uranium metal had to be purer in order to achieve a moderated chain reaction. This problem would be solved in 1940 with the invention of something known as the Ames process that would be able to produce reasonably large quantities of very pure uranium oxide metal. To create a weapon, on the other hand, what one needed to do was get a large quantity of material that would spontaneously undergo a chain reaction if enough of it was brought together in a small enough space. That's this thing we call critical mass. In order to do this in 1939-1940, the idea was that the U-235 would have to be separated from the U-238. Now normally, when you want to separate two different elements, you can use some sort of chemical reaction process on a sample to isolate one specific element from the other. This is the kind of thing that Marie Curie had developed in order to isolate radium from that mountain of Austrian sand just 40 years earlier. The problem with that approach here is that isotopes are chemically identical, so those kinds of processes won't work. In order to do isotope separation, you have to use a method that will rely on the very slight difference in the masses of the two isotopes. One such method, as you may recall from an earlier episode, is to use a powerful magnet to create a mass spectrometer. The U-238 will travel in a slightly larger path than the U-235 and thus will separate out. Other methods, such as a gas diffusion method, would be developed in Britain to try and tackle this problem. This was some of the work Paul Dirac contributed to during the period of the Blitz. However, in 1940, another solution would present itself, and this is where the reactor research begun earlier became so important to the story. In Britain, Egon Brecher and Norman Feather were able to show that in a U-238 reactor, U-238 atoms would absorb some of the neutrons emitted from the U-235 fission events if those emitted neutrons had just the right amount of energy. If that happened, the process of new element creation would take place in much the way that Fermi had thought had taken place back in his 1934-1935 experiments. Later that year, Ernest O. Lawrence and his team of researchers at the University of California, Berkeley, namely Glenn Seaborg, would use the cyclotron there to accelerate deuterium atoms to a speed that was high enough to penetrate the uranium nucleus and create those two new elements. At nearly the same time, similar research was taking place in Britain under the direction of Nicholas Kemmer. The first of these elements was named neptunium, while the second was called plutonium. Due to its nuclear composition and structure, plutonium was expected to have many of the same properties as U-238, only more energy would be released in the fission event. This is why Fermi's reactor research became so important. It provided a second way to produce fissile material for weapons construction. When the first pile went critical in 1942, it was a huge step in that direction. Now, before we go much further, we should take stock in where things were and the efforts in or around 1942. In Germany, while a good deal of work had been done between 1939 and early 1942, the situation had changed by the spring of that year. Due to setbacks on the Eastern Front, it was becoming clear that Germany was in for a very tough fight with the Russians. As such, an administrative decision was made to scale back on work related to nuclear energy, as it was realized that it was fairly unlikely that without massive industrial investments in either isotope separation or in uranium production for reactor work, a great deal of progress would be made. As such, much of the project funding was cut, and those involved in the work, such as Heisenberg, moved it to something more along the lines of regular scientific research. During 1942 in the United States, as the pile work in Chicago began to show progress towards the goal of producing a self-sustaining reaction, the work of the S1 Committee was assumed under the direction of the U.S. Army's Corps of Engineers. General Leslie Groves, who commanded the Manhattan District of the Corps, headed this new collaboration, and thus the project was dubbed the Manhattan Project. One of the best decisions he initially made was that he didn't actually have the time to make a specific decision on which technology paths to take, and he did have the resources to follow them all. Thus, Groves pursued both the uranium-235 isotope separation solution to bomb production and the plutonium generation reactor solution to bomb production. The project was divided into four main groups. There was the Metallurgical Lab at Chicago, which was responsible for reactor research and plutonium research. There was Oak Ridge Laboratories in Tennessee, which oversaw multiple methods of isotope separation and then later on, plutonium production. The Hanford Nuclear Reactor Site, which was constructed in eastern Washington state to produce plutonium once the technical issues had been worked out in Chicago, and also to do element separation once the plutonium had been produced. And then finally, there's the group most people are most familiar with, the Theory and Design Group on the Mesa outside of Los Alamos, New Mexico. In 1943, a number of suspicions were ironed out between the British bomb project, that Tube Alloys project, which had begun reactor research in Montreal, Canada, and the U.S. Manhattan Project, and the two were joined together. In 1944, the Hanford reactors were brought fully online, with both the breeder reactors working to produce plutonium within the uranium-238 fuel, and complex chemical separation operations working to extract that plutonium from a toxic stew of radioactive fission byproducts. Once this portion of the process was running, many of the team at the Metallurgical Lab were transferred to Los Alamos to assist with the work on design and fabrication of the bombs. One of the long-standing questions was just how much fissile material was required to create an explosive, self-sustaining reaction. Early in the process, British scientists had done a rough calculation from using U-235 and found the quantity to be on the order of just a few kilograms. In Germany, Heisenberg had originally calculated that an enormous amount of U-235 would be needed, something on the order of 500 kilograms. But the evidence suggests that sometime after 1940, but before Bohr fled to Denmark, he had redone the work and had reached a much smaller number. Whether this was ever shared beyond the scientific working group is a matter of some historical debate. Moreover, whether Heisenberg was disinclined to share information with the Nazi political apparatus out of moral objections or due to pragmatic concerns is also a subject that is contested amongst historians. There is evidence that he was afraid that if he shared the number with individuals in the Army, that there would be expectations that the scientific team would be able to deliver a weapon in fairly short order. His fear was if they knew it, and if his team failed to do that, the repercussions could be severe for the individuals involved. As the projects in the UK and the US progressed, both teams independently arrived at a number around 10 kilograms of fissile material as being required in or around 1941. The next issue was how to create a weapon where the material would only go critical and explode when desired. This led to two very different solutions. The first, used for the bomb designed around uranium-235, was to have two smaller subcritical pieces of material in the bomb. One of these pieces would be fired a bit like a bullet from a gun into the other piece. When the impact took place, the two pieces of metal would fuse together, and the combination would be large enough to exceed the critical mass threshold, thus setting off an explosion. For the plutonium design, however, it turned out that a more complex solution was required. What was needed was an ability to have a subcritical mass that could be made to go critical without having to use the gun design. The way it was decided to do this was to rapidly compress the plutonium until the density was high enough to take the material over the criticality threshold. In order to do this, the design called for the plutonium to be placed at the center of a shell of high explosives that, when ignited, would create a spherically symmetric shock wave that would push inward to create the compression. This turned out to be one of the most complex problems of the project to solve. By 1945, the reactors in Hanford and the isotope separators in Oak Ridge had produced enough fuel for 2 plutonium weapons and 1 uranium-235 weapon. Due to the complexities and uncertainties of the plutonium design, it was decided to test it to make sure that it would work. On July 16, 1945, the first atomic bomb was detonated at Los Alamogordo in New Mexico. Called the Gadget, the bomb exploded just as designed, with an estimated yield equivalent to some 16 kilotons of TNT. In this moment, the world and the discipline of physics crossed a threshold that has forever changed our perception of many things. It is with a consideration of these changes that I would like to conclude this episode of the podcast. Before I go further, I would like to say that I understand that for many of my listeners, the subject of the development and deployment of the first atomic and later nuclear weapons is a topic of great passion where strongly held ideas and opinions often hold sway. I do not plan to discuss the question of whether the bombs should have been used in Japan. For those interested in such a podcast examination, I would recommend Dan Carlin's Hardcore History episode titled Logical Insanity. What I'd like to do instead, as I finish here, is consider what the implications of this decision were for humanity and the scientific community, especially for the community in physics. Historically, the Second World War is often referred to as the Physicists' War. There are a few reasons for this, but the biggest is the contribution physicists made to developing technology that profoundly influenced the prosecution and outcome of the war. This goes well beyond the technologies discussed in this podcast. A very strong argument can be made that the most consequential contribution made by physicists was the development of radar. As one scientist said with some justification, the bomb may have ended the war, but radar won it. Even as true as this may be, it is the development and detonation of the bomb over Hiroshima first and later Nagasaki that catapulted the physics community to the forefront of the public stage. Leaving the horror of the development of the weapon aside for a moment, it is the creation of the technology in a mere 6.5 years from barely discovered and understood phenomenon to fully actualized utilization that is a truly remarkable accomplishment, one attributed almost entirely to physicists. Moreover, it was understood that while the project was, for a significant amount of its time, under the direction of the U.S. Army, it was the scientists who made most of the decisions regarding the work and advised the military on almost everything else. No one would have thought that, in 1925, the U.S. or world physics community could do anything close to influence what they would by the late summer of 1945. In conjunction with this increase in influence came enormous increases in funding and oversight. While the era of big science can be said to have started as far back as the early 1930s, it is during the war that the financial resources allocated to big science reached truly staggering levels. Levels, it should be noted, that would continue to grow after the war as both an arms and technology race developed between the two superpowers and their associated partner states. In this race, scientists of all stripes, but especially physicists, became resources to be developed and mobilized in service of the state when required. As a result of this, there would be a huge increase in the number of physicists, something that would accelerate the pace of discovery and application in the years following the war. Many of the techniques we will discuss in the next episode of the podcast that were used to develop renormalization theory were based on method used to solve problems that faced either the radar team or the theorists working at Los Alamos. There was, of course, a downside to this as well. As the implications of the bombing began to weigh on the minds of the scientists involved in the development of the weapon, there was a movement to make sure that the technology remained under civilian control. In the late 1940s, several scientists that were originally associated with the Manhattan Project joined together to promote an agenda that would seek to promote peaceful uses of the technology. One successful outcome of this effort was to have the structure of the Manhattan Project switched over to a civilian agency known as the Atomic Energy Commission that would be responsible not only for weapons construction and research, but also reactor-based research and energy production. Less successful, however, was the attempt to share the technology with all interested parties or to have it regulated under the auspices of the United Nations. These attempts brought several scientists under the suspicion of their various governments, with dire consequences for some. The most famous case of this was that of Robert Oppenheimer, whose pre-war sympathies towards communism and post-war activism in various causes led to a loss of his security clearance to work on any project associated with any of this, effectively crippling his career. Moreover, several of his graduate students were painted with the same brush and were never able to be successful professionally. More globally, the development of the first atomic weapons caused a number of people in the scientific and engineering community to pause and consider the type of work they were doing. Many asked if they had a responsibility to consider the applications of their research and if they might be ethically bound to only pursue lines of inquiry that would lead to outcomes that were broadly beneficial. In this post-war climate, there were recriminations and accusations by and against those who worked to produce such a terrifying technology, just as there were those who strongly asserted that not only was such work proper, but that it was the duty of a scientist as a citizen to do what they could in defense of their nation. This led to questions of whether a scientific identity was national or should it be more global. As I discussed in the first series of the podcast, science has come to the conclusion on some of these questions. Pure science, I think, must pursue a knowledge or understanding of the physical universe without regard to possible consequences. It is nearly impossible to determine what the application of a particular line of pure inquiry will lead to. In the areas, however, of applied science and engineering, the answer is less clear, though there is a sense that much of it lies more in the realm of value inquiry than in scientific inquiry. As for where a person's loyalties lie, that is still a really unanswered question. Once the physicists showed themselves to be excellent weaponeers, they became of tremendous interest to the governments of the world. As such, it is unlikely that physics will ever return to those early days in the 1900s when just 500 or so practitioners plied a trade that few politicians took notice of. Pandora's box, as it were, has been opened, and from that point onwards, there would always be pressure, and there will always be pressure, to serve the aims of the state's interests, especially when the state is funding a lot of the research and training. Nevertheless, there is also a sense among almost all of those who study nature that there is a loyalty to something bigger and more universal than just a government, no matter how well-meaning that polity might be. There is a sense of either discovery or service to humankind that pulls the scientists now beyond just a consideration of what's the best thing for them to do to what's the best thing for all. It is, I think, a lasting legacy of the bomb and other technologies of the Second World War that many scientists feel that they must think bigger and more broadly about the work they do. The work being done is thought to matter, perhaps, very profoundly, and so there is a sense of deliberateness when considering what new genie will be released when a new line of research is pursued or a new technology developed. More than that even, there is a rejection of the principle of scientific separation practiced by Heisenberg and many of his colleagues that removed from the public square the voices of those whose work might be used in ways that would be deeply objectionable. For me, this is a positive outcome of all that has been discussed in this podcast. Until next time, full sails on your journey.